Good morning. Welcome to the Minnesota Commerce Department webinar on Small Embedded Data Center Pilot. This presentation is being provided by a grant from the Conservation Applied Research and Development. I want to let you know that the attendees will be in listen-only mode. We will use a text box to ask questions, or if there's a problem with audio or visual, please enter it in the text box to the right of your screen. We will try to answer all questions during the presentation. The presentation is being recorded and will be made available along with the CDEC final report to all participants. It will also be available and posted for public access. With that, I would like to introduce you to Mary Sue Lobenstein, who is an R&D Program Administrator for the Minnesota Commerce Department. Mary Sue?
Welcome to this Conservation Applied Research and Development, or CARD webinar. As Jenna said, I'm Mary Sue Lobenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. And this webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund. The Applied Research and Development Fund was established in the Next Generation Energy Act of 2007. Its purpose is to help Minnesota utilities achieve their 1.5% energy savings goal by identifying new technologies and strategies, improving the effectiveness of utility conservation programs, and documenting CO2 reductions from conservation programs. $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal, or RFP, process. Since the legislation was enacted, the CARD program has had 8 funding cycles with 22 RFPs posted, received nearly 380 proposals, and funded 92 projects, representing over $21 million in research dollars. And as you can see by the pie chart, projects funded to date have been in all building sectors. The subject of today's webinar is in the commercial sector and reports on the results of the Small Embedded Data Center Program Pilot. It will be presented by Lester Shen of the Center for Energy and Environment, Janet Lynch-Eisenhut of the Wisconsin Energy Conservation Corporation, and Jon Vanyo of the Minnesota Technical Assistance Program. So I'll turn it over to Lester to get us started.
Hi, I'm Lester Shen. I'm the Director of Innovative Technologies at CEE and served as the Principal Investigator of this study. The project team consists of CEE, who are the project lead, and our project partners were MnTAP, WECC, the Foundation, a single-source IT service provider, and Packet Power, who offer data center power monitoring systems. The pilot program was performed over a 2.5-year period and consisted of a characterization of the Minnesota SEDC market via an electronic survey administered and analyzed by WECC in the first half of 2015, a field study of a number of participant sites performed by CEE and MnTAP from late 2015 to early 2017. The final report was produced by CEE in the spring of 2017, and the pilot project results are being presented today in this webinar. The agenda for today's webinar will cover first an overview that describes why we are doing this project and what was involved, followed by a presentation of the results of the market characterization, a description of how we recruited the participants for our field study, the findings of our field study, and finally, the recommendations that we have drawn to increase energy savings for SEDCs. So now I'll provide an overview of our project. Data centers are responsible for nearly 2% of the total electricity in the U.S., and small embedded data centers, or SEDCs, represent about half of this energy use. Studies have found that SEDCs use much more energy than is necessary to provide the IT services that are required, representing an important opportunity for greater energy savings. SEDCs are typically found in a room or rooms of the building where the host building or institution resides and can serve that building or a campus of buildings. SEDCs are not only server rooms but can also be network closets or intermediate distribution frames, also known as IDFs, that are located at several locations in the building or throughout the campus. SEDCs are one of the fastest growing end uses of electrical energy in commercial building. Let's look at how electricity flows through an SEDC. AC power comes from the electrical panel to an uninterruptible power supply, or UPS, which is basically a battery backup system. Electricity then flows to the power distribution unit, or PDU, which distributes power to the IT equipment of the SEDC, such as servers, storage devices, network switches, and other devices located in the server racks of the SEDC. The network switches provide power to data ports that serve workstations and network office equipment, and power over Ethernet or PoE devices like phones and Wi-Fi access points. IT equipment in the SEDC generates heat, and if inlet server rack air temperatures exceed the range recommended by ASHRAE, dedicated cooling equipment is required. ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers and is an engineering professional organization that establishes industry standards. The cooling equipment includes rooftop units or RTUs, ductless splits, or computer air conditioning units or CRACs. This project was composed of 5 tasks. The market characterization performed by WECC, 2, recruitment of the field study participants by CEE and MnTAP, 3, the field study in which MnTAP worked with the industrial sites and CEE worked with the commercial and institutional sites, 4, the field study findings were performed by CEE and MnTAP, and 5, the dissemination of our results through the final report and webinar were performed by CEE, WECC, and MnTAP. I'd now like to turn this over to Janet to discuss the characterization WECC performed of the SEDC market in Minnesota.
Thank you, Lester. The market characterization process included a review of prior studies and working with partners such as CEE and MnTAP to identify potential CDEC participants. It concluded with an electronic survey to identify barriers and opportunities of CDECs, and these barriers were considered items related to downtime and mission-critical equipment concerns, budget and staff limitations, lack of technical expertise, and how decisions were made to upgrade or replace equipment, as well as number one priority regarding security. Opportunities were related to how to reach decision makers and help staff understand options for equipment operation. We were also looking to see areas of potential energy savings and the importance of vendor support. There were 134 responses to the distributed survey, and responses were filtered to 82 that were defined as CDECs, or small embedded data centers. This included server closets, which was typically under 200 square feet, and rooms, which were under 1,000 square feet. As you can see from the map on this slide, there was a wide area of survey respondents with a significant group in the Twin City metro area. Based on the survey responses, pilot participants were identified. The survey was used to determine best practices to reach CDEC market by identifying energy efficiency opportunities for utility offerings, addressing CDEC business barriers, and by defining a role for trusted sources. Of the 82 CDEC survey respondents, 15% were government entities, 30% were in the manufacturing sector, and the majority, or 38%, were in the other category. This category included many different types of businesses, including nonprofits, real estate, software, research, construction, hospitality. Overall, a pretty wide dispersal. To better understand how a CDEC business structure consisted of, the survey asked how many of their employees were located on site. 30% of the respondents, which had under 200 employees, 13% had 100 to slightly under 200 employees, and 54% had under 100 employees. So the majority had under 100 employees. The most frequent building type for survey respondents, or 35%, was a standalone building or unitary business. Manufacturing facilities were 29% of these respondents, and office complexes were 21% of the respondents. This slide represents the number of server racks associated with the businesses. Almost all businesses use less than 10 servers, and half of the businesses had a single server rack. Virtualization is now a fairly standard practice with the CDEC respondents. It allows for a single server to be used to host multiple virtual machines to run a variety of applications, including addressing redundancy and power usage. Server virtualization is a system configuration available for over a dozen years and can contribute up to a 40% energy savings for IT systems based on a published study by Whitney and Delforge in 2014. Cloud services are ramping up as an alternative to redundant server systems as well, but respondents had indicated an increased concern for security associated with cloud services. This slide gives you a bar graph to represent CDEC respondents and how they have adopted new technologies such as virtualization and cloud services, as represented by the 60% who monitor server utilization. Of this majority, only about half of the server closets, and that's the ones under 200 square feet, use virtualization, while a majority of server rooms, which is anything under 1,000 square feet, use server virtualization. A minority of all CDEC respondents monitor power usage, which will provide additional energy efficiency opportunities, especially since 90% of all the electronic survey respondents pay utility bills and could benefit from additional incentives. Industry reports that an average IT equipment refresh cycle is about 3 years. For CDEC respondents, 39% indicated they had server equipment over this average age, which presents an opportunity for equipment planning and replacement. 43% of respondents have equipment in the industry average range, and that's how this slide kind of represents. So overall, there's some very aged equipment out there, especially with the smaller closets versus the server rooms. A big opportunity is to reach the appropriate decision makers to make them aware of utility incentives to offset cost restraints. Survey respondents were interested in a free on-site energy audit, and around 1/2 expressed a willingness to invest in energy efficiency that resulted in savings on their utility bill. Some of the barriers to investing in energy efficiency technologies were resource constraints, 23%, priority, 18%, and operational risk, 18%. We also noted that vendors were the most important trusted source of information that affects equipment replacements, planning, and improvements. Vendors would also be a key to promote energy efficiency to CDEC decision makers associated to system planning, operation, and investment. With that, I'd like to introduce Jon Vanyo from MnTAP.
Fortunately, we can't get John to, John can't get his muting undone, so I will present his part. In regard to the characterization survey, this survey was extremely useful for recruitment. The survey was emailed to CEE and MnTAP contacts, utility customers, and was available online. One of the survey questions asked whether the site was interested in a no-cost data center energy assessment. Sites that answered yes were added to our outreach list for the project. We then sorted through our other responses in an attempt to get a good distribution of small data centers in Minnesota. The final step was to call or email these sites to schedule an energy assessment. After initial interest was generated in the survey, recruitment was very easy. There are many IT professionals who are interested in saving energy and operating efficiently. In total, 11 sites participated in this project. The typical site had 0.9 server rooms and 1.3 intermediate distribution frames. The typical server room had 4 racks, while the typical IDF had 2 racks. You can see the distribution of sectors that participated. We worked with architectural design firms, healthcare, legal services, a municipality, a nonprofit, school districts, and a few manufacturing sites. Next is a field section study. I'll be describing the assessment process right now. The next step after recruitment is a site assessment. We meet with the site contact, explain the project, and answer any questions. We then complete a walkthrough, collecting information on the IT and cooling equipment. We're collecting information like make and model numbers, amount and types of equipment, how often things run, and temperature set points. After collecting this information, the next step is to install meters.
So, in the next slide, you'll be able to see the packet power plug meters. I guess my introduction, my name is Jon Vanyo. I'm an associate engineer at the Minnesota Technical Assistance Program. And so here we are. On the left, you can see the packet power plug meters that we use throughout this project. They're very simple to install. You plug the device into the meter, and then you plug the meter into the wall. The meter sends a wireless signal to a gateway, which then connects to the web via Ethernet cable and provides access to the energy information. There are slightly different plug meters based on the voltage and current of the devices being measured, but generally they're pretty easy to use. Because most of the IT equipment is run off of a universal power supply battery with redundant plugs, we were able to install these meters without depowering equipment or taking the server room offline. This was very important to the IT staff who preferred to keep their equipment online as much as possible. That being said, we did schedule the installs at off-hour times when IT equipment was not critical, just in case a redundant system did fail. And then on the right, you can see an example of a piece of equipment that doesn't have a wall plug. So in-panel current transducers were used to collect the energy information that we needed for the project. These were commonly used to measure HVAC energy consumption. After installing the meters, we collected a few weeks worth of data and then began analyzing that data in order to identify energy savings opportunities and to calculate energy savings potential. We then shared these savings opportunities with our site contacts in order to promote implementation. In the ideal cases, we were able to also use the meters to measure the energy savings from the project prior to uninstalling the meters. And that was our field study process. So next we're going to get into what we found in these server rooms. Some things are very common between small embedded data centers and some things vary. The equipment you're likely to find in a server room includes servers, switches, storage, and universal power supplies or UPSs. However, when we started looking at cooling, things were much more variable. We worked with a site that had a computer room air conditioner under the floor. One site had in-row cooling. There were a few rooftop units and some ductless splits. There was even one site simply using an exhaust fan to pull air over servers to keep them cool. The average server room in this study draws about 4,500 watts and costs roughly $4,000 per year in electricity. The average IDF had an average load of about 900 watts and costed about $770 per year in electricity. And the final point I will leave you with is that none of the sites we worked with had 24/7 business operations, but most IT equipment is left on 24 hours a day, 7 days a week. It became clear by analyzing the energy data that there is an opportunity to save energy by scheduling IT equipment to turn off or stand by during off hours. And with that, Dr. Shen will be diving even deeper into the findings and conclusions of the project.
I'd like to further address the third finding that John described. This graph shows the power load of an SEDC at one of the participating sites over 1 week in April. The graph shows a fairly constant power load with 5 peaks occurring during the working hours of the office from Monday, April 3rd through Friday, April 5th of the work week. All of the SEDCs in this study showed the same behavior. For this site, as server utilization reached its maximum during office hours, the load increased by as much as 10%. During the nights and weekends when the office was unoccupied, the power load remained constant. Basically, the SEDC has a base load of 3.1 kilowatts. Notice that almost 60% of the week, when no IT services were called for, the SEDC was responsible for about 3 kilowatts of phantom loads in the building. There's a significant opportunity of IT savings just through operational efficiency. Using a residential analogy, we need to find ways of turning off lights and reducing phantom loads when the office is unoccupied. As part of this study, we wanted to see if there might be a way that we could disaggregate the power load by estimating the draws of the various IT equipment in the SEDC. This would be useful for developing an audit form and estimating savings opportunities. In 2016, Lawrence Berkeley National Laboratory, or LBNL, published a study on U.S. data center energy usage in which they determined typical power draws for servers, storage devices, and network switches. We used these values to test a way of estimating total SEDC power draws for our participating sites. In addition, we also used typical power draws for other IT equipment in the service racks, as well as for typical PoE devices like phones and access points that drew power from the network switches. This approach allows us to estimate SEDC power load by counting servers, hard drives, network ports, and PoE devices. The graph shows a comparison of the estimated values versus the actual measured power loads of each SEDC in the study. The diagonal line represents exact agreement. The good agreement shown in this graph suggests that this approach could be used to calculate deemed savings for IT measures. Let's now look at some specific measures. All power going to the server racks first goes through the UPS. AC power is converted to DC for the batteries in the UPS, and then converted back to AC as it feeds the PDUs of the server racks. This adds some inefficiency, and as a result, increasing the efficiency of the UPS is an important and appreciable opportunity for savings. This graph shows the efficiency of a typical UPS versus the percent power load on its battery capacity. For this study, the average UPS percent load was about 40%, or about 80% efficiency, with over 50% of the UPSs having a percent load of 40% or less. Often, we saw SEDCs with a number of UPSs that all had low utilization, or one larger UPS that was well oversized. Steps could be taken to consolidate the multiple UPSs into one higher utilized UPS, or the oversized UPS could be replaced with a properly sized UPS. By increasing the UPS utilization to 60 to 80%, the SEDC could immediately obtain a 5 to 20% savings. Now let's consider some specific IT equipment measures. Firstly, servers often are dedicated to a single application or function, like an email server or a database or a specific program. When that application or function is no longer needed, often the server is still kept running, just in case that it might someday be needed, but actually is not used at all. This server can be considered a dormant or comatose server. At one of our sites, turning off a dormant server brought annual savings of about 1,200 kilowatt hours. The LBNL study found that the average server power draw is about 330 watts. A study by the Natural Resources Defense Council, or NRDC, estimates that up to 30% of the servers in SEDCs are comatose. 2. The number of physical servers can be reduced through server virtualization. Virtualization creates multiple servers to operate on one physical server. At one site, consolidating servers through virtualization resulted in the removal of the 7 Xserves, with a total power load savings of 3 kilowatts. Finally, server management software exists that allow virtual servers to migrate between physical servers. This is useful when an SEDC needs multiple physical servers to run their virtual servers during high activity. However, during low utilization, these virtual servers can be migrated to fewer physical machines, ready to be called to action, but also allowing the other physical servers to be put on standby when not needed. This was performed at 2 sites, resulting in savings of 0.6% and 9%. Network switches reside in both server rooms and IDFs. Even as more IT services go into the cloud, services go into the cloud, network switches will be needed to provide network services throughout the organization. Each data port of the network switch is connected to network-connected devices like workstations, printers, phones, and Wi-Fi access points. Each data port draws about 2 to 4 watts, and switches typically have 24 or 48 ports. SEDCs also provide low-voltage DC to actually power devices connected to the Ethernet cables. This is known as Power over Ethernet, or PoE. These PoE devices include phones and Wi-Fi access points. Each phone draws an additional 2 to 4 watts, and access points draw another 8 to 10 watts. Switch manufacturers actually provide energy management software that IT staff can use to schedule power to specific ports and turn off power draws during off hours. This was not done at any of our participating sites. 2 sites did perform this measure for this study, benefiting from the expected savings. The savings from network switch scheduling can be particularly appreciable when institutions have thousands of phones and hundreds of access points in their campuses of buildings. Now let's consider cooling savings opportunities. ASHRAE recommends that server rack inlet temperatures are maintained in the range of 64.4 degrees Fahrenheit to 80.6 degrees Fahrenheit. Consequently, thermostats could be adjusted to set points that deliver air temperatures as high as 80.6 degrees Fahrenheit at the front of the server racks. Most of the SEDCs with dedicated cooling in this study have their thermostats set at temperatures in the low to mid-60s. With knowledge of the rack inlet temperatures, energy savings opportunities exist by reducing the cooling load of the SEDC through more efficient delivery of cool air to the server racks, and consequently by raising the thermostat set point temperature. At 3 sites, we were able to increase the thermostat set point temperatures 3 to 4 degrees from the mid-60s to the upper 60s. This resulted in cooling load reductions ranging from 7 to 50%. At 2 sites with RTUs, we found that during times with no cooling load, the air handler was running continuously. Changing fan settings at the thermostat from on to auto resulted in a 95% reduction in energy use of running the air handler at one site and an almost 60% savings at the other site. From our temperature monitoring, we found that in SEDCs with dedicated cooling, there was a lot of mixing between the cold air supplied to the rooms and the heated air exiting from the server racks. This resulted in high uneven temperatures measured at the front of the server racks. Cold and hot aisle containment can not only reduce cooling loads, but also ensure better control of server inlet temperature. An especially interesting example of this was provided at the site that used a 750 CFM exhaust fan to remove heat from the server room. The fan drew about 300 watts. Conditioned air was drawn from the rest of the office through a grate in the door. The power load of the SEDC was about 4 kilowatts, and server inlet temperatures reached as high as 86 degrees. Plastic drapes were installed to create a contained hot aisle where the exhaust fan could remove the heated air. This measure resulted in inlet rack temperatures in the range of 75 to 78 degrees. The cost of the plastic was less than $100. The site was planning on installing dedicated cooling, and this measure avoided HVAC work estimated to be in the tens of thousands of dollars. This also raised the possibility of putting the exhausted waste heat to more productive use elsewhere in the building. Finally, as an example of the savings opportunities from the IT measures, let's consider the average server room that we encountered in this study. It had 5 server racks with 3 UPSs, 11 servers, and 7 network switches. The power draw for this average server room was about 4.5 kilowatts. As an aside, the average server room in this study also had 9 storage devices containing a number of either hard disk drives or solid-state drives. We were not able to look at energy savings measures of data storage, but believe that this could be an area of further study and savings opportunities. First, let's consolidate the 3 UPSs, which are running at less than 40% utilization, to 1 UPS at 70% utilization. This would result in an average of 10% in UPS efficiency for a savings of 452 watts and a 10% reduction in power draw of the SEDC. Next, let's look at the servers. Since the NRDC study estimates that up to 30% of the servers in an SEDC are dormant, let's assume that we can power down 3 of the 11 servers, each with an average power draw of 330 watts. That brings an additional savings of 990 watts and a total savings of about 32%, and a reduction in server power draw of about 1.5 kW. An additional comment can be made about the SEDC cooling load. Firstly, the 1.5 kilowatt reduction in power draw equates to less heat dissipated into the SEDC, and hence a reduction in the cooling load. The cooling load of an SEDC is typically about the same as the IT load, So a similar 1/3 reduction in cooling load will likely also result from these two measures. For the network switches, we can schedule 5 of the 7 network switches. If we can schedule 5 of the 7 network switches to power down the data ports and PoE during night and weekend hours of no office activity, then during those non-work hours, we can achieve an additional power savings of about 480 watts, or 43% total. Finally, if during non-office hours we migrate virtual servers to only a few physical servers, placing the remaining physical servers on standby, then assuming a 10% power savings, the total SEDC power reduction during off hours would be about 2.1 kW, or 46%. To summarize, during the work week, these measures would result in a 32% reduction in power load. During the remaining non-work hours, basically overnight and on weekends, or about 60% of the total hours in a week, a 46% reduction in load would be obtained. A similar effect would result on the cooling load. Based on the findings from this project, I'll now summarize our major recommendations. We have the following recommendations for IT staff. Firstly, it is important to monitor data center power loads and server air temperatures to determine how much additional energy your data center is using to deliver your mission-critical services. This would include monitoring UPS power loads and server inlet temperatures. Secondly, efforts to reduce baseload IT power or phantom loads can be taken by identifying and turning off comatose servers, consolidating servers through virtualization, and reducing unnecessary storage. During times when mission-critical services are not in demand, operational efficiency measures through scheduling and energy management can be employed. 3, when the time comes for equipment to be updated or replaced, more efficient models should be purchased, such as Energy Star rated equipment, and proper equipment sizing should be specified. Finally, options such as cloud services or co-location should be considered. The PUE of SEDCs are typically on the order of about 2, while cloud services are reporting PUEs as low as 1.1 to 1.2. This could be used as a basis for counting carbon reductions by going to the cloud. With regard to utility programs, first, since survey results found that only 2% of IT staff were aware of utility rebates and incentives, there's a clear need for utilities to raise awareness of IT staff responsible for SEDCs. 2, the ease of monitoring SEDC power draws into the UPS can be used to assess measured savings and provide a basis for a pay-for-performance program. In addition, the typical power load numbers presented by the LBNL study can provide a good basis for deemed savings of energy measures, such as server consolidation or network switch scheduling. These numbers can also be updated over time as more measured savings data is collected. 3, the survey also found that the trusted sources of information for IT staff were vendors and service providers. Midstream approaches that take advantage of these information channels as well as incentive energy efficiency choices could be effective. 4, along these lines of midstream approaches, an SEDC design assistance program could be delivered to architectural and engineering design firms to help guide the design and construction of more energy efficient server rack layouts and crack systems in buildings with SEDCs. Finally, utilities currently have recommissioning programs, and the HVAC measures that can be used to deliver more efficient cooling in SEDCs could fall under these programs for custom rebates.
Thank you, Lester. That was very nice. At this point, what we will do is we will review some of the questions that have come in from the participants, and we'll also address some other questions that came in from a prior presentation so that we can share that with today's participants. One of the first questions that was asked was, how do you identify a comatose server? It was referenced several times in your presentation.
Basically, you have to talk with the IT staff to determine what applications aren't being used and identify which servers are running those applications. So you have to communicate pretty closely with the IT staff on that.
All right. Another question was, if the average room only had 1 to 4 servers, how were they using the 4520 watts that was represented on one of the slides?
The average server room had 4 server racks, and so each server rack can have any number of servers, switches, etc. within them.
Okay.
Thanks, John.
All right.
No problem.
Okay. There was also another question on, were the plastic curtain panels approved by the fire code officials?
For those, we just tested the setup and used the plastic sheets that are typically obtained for the purpose of creating those doors or barriers for grocery stores and convenience stores. So according to the specs that are used for those spaces, those were the ones that we used. I think that more work needs to be done to check about the fire codes for server rooms, but we also went kind of with common practice that we've seen with larger data centers that have used these.
Great. Another question that we had was, did the LBNL, the Lawrence Berkeley study, also cover KW use, such as runtime hours or the percentage of the average load? I know you referenced that in some of your presentation as well.
From what I understand, the LBNL study got that data from measured usage from servers. So it's I believe it's just the typical loads that they monitor.
Great. I think that was all the questions that we had for today. I do want to mention a couple other things. We apologize for any other technical difficulties that may have occurred. There was a mention on we kind of misrepresented UPS as universal power supply. However, in one of the prior slides, it was identified correctly as uninterruptible power supply. So we did have that. And with that, I think what we're going to do is go back to Mary Sue Lobenstein, who will complete the presentation for today. Mary Sue?
Yes, thank you, Janet. And thank you, Lester and John, for all three of you for presenting the results of this card study. Really appreciate it. You can download the final report on this project from the direct link on this slide, which is over on the right there. And the link for the card web page is also on this slide. The web page has various resources and information related to the card program and to card research projects, including links to this and other recorded card webinars and final reports. Use the quick links indicated to help you navigate to what you are looking for. So thanks again for participating in today's study, or in today's webinar. We really appreciate it. Before we leave, I want to take an opportunity to mention a couple of upcoming card webinars that might also be of interest to you. One is this coming week on Wednesday, July 26th. There's a webinar by Illum Advising on the statewide commercial behavior segmentation and potential study project. Then on August 17th, the White Group will conduct a webinar on a pilot program which investigated an option for expanding utility new construction design assistance programs to smaller utilities statewide. Please contact me if you want more information on how to sign up for any of these webinars, or if you have questions or feedback on the card program, please feel free to contact me. Thanks again, and have a good morning.